In this video, we are going to look at addition reactions and also polymerization. Here are some of the definitions that you will require: hydrogenation, electrophile, and carbocations, primary, secondary, and tertiary. These definitions can all be found on the SIA AS glossary. Electrophilic addition. The main reaction of alkenes is addition. We've already looked at the structure of an alkene and looked at pi bonds. Because of the high electron density, alkenes are attracted to species which like electrons. These are referred to as electrophiles. In the spec, it says that you have to recall that the carbon-carbon double bond is a center of high electron density. We are going to now look at the mechanism of electrophilic addition. This mechanism is very different to the mechanism we met in the topic previously, where we looked at free radical substitution. We are going to draw a mechanism. Here is a mechanism below, and just to go through different points, we're going to use curly arrows, and curly arrows are the movement of a pair of electrons. We're going to show any dipoles in our molecules. When we have a positive charge, that is a full positive charge, and that is on our carbocation. And if we have any negative ions, we show the lone pair as shown on the bromide ion. The first mechanism we are going to look at is in the reaction of ethene and bromine. We studied this reaction at GCSE as we used this as a test for a carbon-carbon double bond. If you remember, we do this reaction at room temperature and we don't need a catalyst or UV light. Let's have a look at the mechanism of electrophilic addition to work out why this reaction occurs. In the first stage, you have ethene and bromine. Bromine is a non-polar molecule. However, when it is in the environment of the ethene molecule, it forms dipoles. The bromine closer to ethene is delta positive and the bromine furthest away is delta negative. The curly arrow shows the movement of a pair of electrons. The electrons move from the pi bond of the carbon-carbon double bond to the closer bromine atom. The electrons in the bromine-bromine bond move on to the further bromine atom. This bond then breaks, leaving a bromide ion. This is an example of heterolytic fission. We form what is called a carbocation. It has a full positive charge because it has lost an electron to the bromine atom. The lone pair of electrons on the bromide ion move to the positive charge on the carbocation. And we form our product, which is 1,2-dibromoethane. This is the second electrophilic addition reaction we have to study, which is using hydrogen bromide. In this case, hydrogen bromide is already polarized before the reaction begins, but the reaction occurs with the same mechanism. If you have a look, you can see the curly arrow is moving from the pi electrons to the delta positive hydrogen, and that the pair of electrons in the hydrogen bromine bond are moving to the bromine. This bond breaks to form a carbocation and a bromide, and the lone pair on the bromide form a coordinate bond to the carbocation, producing the product bromoethane. If we move on and look at other alkanes, we start to see a problem. Here is an example of propane, which we consider an unsymmetrical alkane with HBr and with bromine. When we react with bromine, we get one product, 1,2-dibromopropane. But when we react with hydrogen bromide, we can form either 1-bromopropane or we can form 2-bromopropane. One of these products is favoured, and we need to work out why. In this section, we're going to look at the addition to unsymmetrical alkenes. In electrophilic addition, the major product is formed via the most stable carbocation. Earlier in the video, we looked at the definitions for primary, secondary and tertiary carbocations. Alkyl groups are electron releasing and can push electrons towards the central carbon, thus reducing the charge density, and this makes the carbocation more stable. So our tertiary carbocation is much more stable than our primary carbocation. Here are the definitions that you will find in your glossary. And below are 2 examples of carbocations. We're going to have a look and decide which one is more stable. If you look at the carbon that the full positive charge is on, in the first example, the carbocation has 2 carbons attached directly to the positively charged carbon. However, in the second example, there is only 1. That means that the first example is a secondary carbocation and the second example is a primary carbocation. So when we do the addition of HBr to propane, we need to look for the formation of the more stable carbocation. If you have a look at the root at the top of the slide, you can see you're forming a more stable carbocation. It is a secondary carbocation. Therefore, that will be the route that is more likely to be taken. So 2-bromopropane will be our major product. Here is a mark scheme tip. You can be asked to explain why a mechanism gives a major organic product. The first thing you need to do is to identify the carbocation. So in this question, it was the tertiary carbocation, and then state that it is more stable than the primary carbocation. So first thing you need to do is identify the type of carbocation and state its stability compared to the other possible carbocation that could be formed. These are a few mark scheme tips about how the mechanism needs to be drawn. If you have a look, make sure that you draw the arrow touching the middle of the carbon-carbon double bond and ending in the region above the hydrogen. In this case, I haven't included the partial charges, but it is good practice to do so. Also remember to draw the curly arrow from the middle of the hydrogen bromine bond. And don't forget both your charge and your lone pair on your bromide ion in the second step of the mechanism. Let's look at some other addition reactions. Again, you met this reaction at GCSE level, the hydration of ethene to produce ethanol industrially. This is done using steam, so the conditions are high pressure and a catalyst of phosphoric acid. Another example is the hydrogenation of ethene to produce ethane. In this case, we use high pressure and a nickel catalyst, which is finely divided, and this reaction is used in the manufacture of margarine. The last bit of this topic is looking at polymerization. Again, this is a topic that you have covered at GCSE. In this case, you are asked to look at the polymerization of ethene and propane. Here are the definitions you will find in the THEA glossary for this part of the topic. Addition polymerization is a method where an alkane undergoes an addition reaction with itself. All the atoms in the original alkanes are used to form the polymer and long hydrocarbon chains are formed. At GCSE level, we learnt how to write an equation for the polymerization of ethene. It's usually at GCSE level a 4-mark question, and it is important to put the N in front of the ethene on the left-hand side and the N in the bottom right-hand corner in the right-hand side. Don't forget to have the double bond in the left-hand side, and you break the double bond on the right-hand side, and you make sure that the bonds cross the brackets. Here are an example of some monomers that we are going to study. The two that are named on your specification are ethene and the second one, which is propene, making polythene and polypropene. One task you can be asked to do is you can be given a part of a polymer chain and asked how many repeat units are in that polymer chain. Pause the slide and have a go.